Okay? Now at some point, like here, I started rounding things off a little because the numbers got big enough that the little things didn't matter, and they really didn't matter to start with, okay? So what we have is here are your x values, here are your y values, same as they were before. To calculate the areas of the trapezoids, I find the y value at the midpoint of each slope segment, right? In other words, I average these two. And those, I think, are right. Okay? And then I multiply that by 1/2, because that's a width, so that's altitude times width, and I get the areas. And then I do the accumulated areas. Okay? By just adding this plus this equals this plus this equals this, and so forth. And that should be pretty obvious. And if it's not, well, you get to do some more trapezoidal graphs. Yeah, they're important. And you'll get used to the process. Okay? So now we want to make a graph. Now, I take my first point, I take my 0 point, and I take my point for x equals 3, and I just plot those in the graph, right? And you just have to trust my scale, but you know, I've specified my scale, and you can see that the numbers sort of match the scale. Okay, so at -1, I'm getting like 2.75, which is pretty close to the, actually I don't have a value for 0, but I got the values for -0.5 and +0.5, which are very close. So they're about here, and well, let's see, -0.5 be about here. So we have a value here and a value here that's only a little tiny bit higher than this one. Okay? At -1, we got a value that's a bit lower than this. Okay? No, actually, okay, it's working out. Okay, at 1, we're getting like 3.2. At 2, we're getting like 6.3. So we have a graph that kind of does this. Okay? Now the basic shape of this graph is this, but spread out. Okay? And it didn't come out that great when I drew it because the way I plotted the points. But it's really, you take about this much of this graph, from about here to about here, and spread it out and stretch it this way, and it's going to look like this graph. Now what's this a graph of? What basic function graph looks like this? I'm sorry?
X cubed.
That's your x cubed graph. Just recognize that instantly. Now you have to raise the x cubed graph up a little bit, because the point where the x cubed graph kind of levels off is the origin. So you have to stretch it out and spread it and then raise it up, and you know what that is if you've had a pre-calculus course that taught you about transformations, so I'm not covering that, although you should really be sure you try to understand why the transformations work, especially why x plus h shifts the thing negative h units. But nevertheless, that's what you have. Now, it turns out that this graph should be about x cubed over 3, and then plus a little something. Okay? Because, put you in the spot again, what's the derivative of x cubed?
3x.
And what's the derivative then of x cubed over 3? Well, if you divide 3x by 3, you get it's 3x squared, right? If you divide 3x squared by 3, you get x squared. Right? So That's what we started with. The accumulated area of x squared is related to the x cubed over 3 graph because the slopes of x cubed over 3 are your values of x squared. Okay? That's a big deal, but you won't remember that from my having said it. But the main point here is know how to construct your accumulated area graph for any given function. By starting with the trapezoidal graph of your function, right? And know how to construct the slope graph. Okay? I think I asked you to do that for the trig functions, and I think I saw some pretty good stuff on it. But, make sense? Now this is a good prelude to calculus because it turns out that the rate of change of this graph, if we did a slope graph for this one, you know what we'd end up with? We'd end up with this. So the slope graph of the accumulated area graph is the original graph. Or close to the original graph if you use a small interval. So I can make a big statement here. And that's essentially the fundamental theorem of calculus. And that's what allows you to do integration. Now, nobody has done much with integration, if anything at all. Okay, but that's where it goes. And this is something you normally learn in the first semester around late October, early November of rigorous calculus course. Okay. And if we could go further with this, we could say that in the limit as your intervals approach 0, the slope graph of the accumulated area graph approaches the original graph. Okay? And then we got to be specific about what we mean by approaches. We'll talk about uniform convergence and stuff like that. But and I'm not going to begin to address that, but from these graphs you can get a good handle on the things you need to understand those things.